Okay, in this segment we're going to start talking about a circuit called the simple current mirror. And given that we're talking about NPN bipolar transistors primarily, we'll be developing the circuit idea in terms of NPN bipolar transistors. But the same circuit can also be made from all sorts of different kinds of transistors. And we'll be seeing this again when we get to CMOS circuits, and we'll see both NMOS and PMOS current mirrors. But for the time being, we're going to be considering two transistors that are connected together in the following way. So we have two NPN transistors, and their emitters are both tied to ground, and their bases are tied together, and we're going to assume that the voltage on the bases for the time being is being supplied by an external voltage source, VB. We'll call this one Q1, call this one Q2, and there's some collector current in Q1 called I1, and some collector current in Q2 called I2. And we're going to say that the voltage on the two collectors are V1 and V2 respectively. And we're gonna start out with some assumptions. Our typical assumptions. Q1 and Q2 are matched. And operate at the same temperature. Okay, those are our typical sort of integrated circuit assumptions. And we're going to assume that VB supplied by a voltage source and we're going to also assume that V1 and V2 are held high enough that the forward active model applies. So that means that V1 and V2 are both greater than or equal to VCE sat. Okay, so obviously in order to have Q1 and Q2 be forward active, we need to have the collector base junctions reverse biased, which means that we would have to have V1 greater than VB and V2 greater than VB, greater than or equal to VB. But we also saw that the forward active model applies also to the soft saturation region. And so V1 and V2 only need to be about 150 millivolts or so above ground in order for that to apply. And so that's the thing that we're going to assume. We're going to assume that V1 and V2 are connected to some other circuitry that will keep the voltages V1 and V2 in this sort of relationship with VCE sat. So we're not showing what these things are connected to at this point, but they are connected to something so that there is a place for the current I1 and I2 to flow from. In other words, V1 and V2 are not open circuited and VB is not open circuited. That's the key thing to keep in mind here. We're also going to assume the transistors are idealized. So idealized transistors. And that's specifically beta goes to infinity and VA goes to infinity. Okay, so that there's going to be negligible base current and negligible early effect. We will be querying these assumptions. In particular, in this segment, we're going to be thinking about what would happen or what would be different if we allow a finite early voltage. And when we develop the full idea of the current mirror, we're going to be also thinking about the effect of the base currents or finite beta. Okay? So with that in mind, our question is going to be, what can we say about the currents I1 and I2. Given these assumptions. Well, one thing we can do is we can apply Kirchhoff's voltage law around this loop. Right, we start at ground, we go up a VB to the base voltage of Q1, and then we go down a VB back to ground. So KVL implies that, say, the VBE of transistor 1 is equal to VBE of transistor 2. Right, so we know the forward active model tells us that for Q1, I1 is equal to IS e to the VB over UT. Right, it's actually VB minus ground over UT. And for Q2, it tells us that I2 is equal to IS e to the VB over UT. And if we simply set these two things equal to each other, the right-hand sides are equal, we find that I1 is equal to I2 regardless of VB. And the box is not quite where I had in mind for it to be, so how about that? So I1 is equal to I2 regardless of the value of VB. So this equation tells us that these two currents should be equal to each other, and that's based on the fact that these transistors are matched and that the voltage on the collectors doesn't matter with respect to determining the collector current. Okay? Now, the actual values of the current will depend on the value of VB, right? So we saw, for instance, that if we were to make the base emitter voltage for a typical type of NPN transistor, maybe around 0.3 volts, 3.35 volts, something like that, we would have a current on the order of a nanoamp, 10 to the minus 9 amps. If we were to increase that a little bit to, say, maybe 0.5 or 0.55 volts, we might find that the currents I1 and I2 are both on the order of maybe a microamp. Or if we were to go up to maybe about 0.7 volts or so, we'd have something on the order of a milliamp. But this relationship between the two currents, I1 is equal to I2, holds over many orders of magnitude of current, regardless of the particular value of IB, or rather VB, and that's kind of a cool thing. So that's our first observation. And so the question is, suppose now that the early effect is not negligible, so VA is less than infinity. Under that relaxed assumption, what can we say? About the two currents, I1 and I2. Well, under these assumptions, now that the two transistors are matched and connected up in this way, but could potentially have differences in their currents due to the early effect, we know that Q1 and Q2 operate on the same collector characteristic. Okay, so if you recall, a collector characteristic is a plot of the collector current versus the collector to emitter voltage. And we're going to sketch a picture of what this common collector characteristic that Q1 and Q2 operate on might look like. Okay, so this is going to be a plot of, say, I1 or I2 versus V1 or V2. And remember, this is a whole family of curves typically plotted on a linear scale where the different curves are labeled each by a different base emitter voltage or a different base current. And so because these two transistors are matched and have the same base emitter voltage, their common collector characteristic might look something like this. All right, so there's a region down near VCE equals 0 where the transistors are in the deep saturation region. And after about 150 millivolts, what will happen is that it shoots up to something that's more or less a constant, or not changing nearly as steeply. I've exaggerated it here probably. And there's a slope of this line. In the first part, we're in the soft saturation region, but then once we get past VB, which might be something like VB, might be here, we would be in the forward active region. So this would be deep sat. This would be soft sat. And then this would be the forward active mode. Forward active region. Okay, so that would be kind of the different regions of operation on this curve. Let's get rid of this for the time being. And so the slope of this line is 1 over RO, the early effect resistance. And if we were to extrapolate this straight line fit back, the y-axis intercept here would be what we called ICO, the 0th order collector current. And then if we extrapolate that back, the x-axis intercept would be minus VA, the early voltage. Okay, so I can't obviously draw that back over here. But, and let me put this at ICO here. If I had a particular value of, say, V1, this curve suggests that I1 would be right here. And if I had a different value, say for V2, let's say up here, V2 would call out a particular value of collector current, let's say I2. And so it should be apparent that one thing we can say is something about the relative values of V1 and V2 and how they map into relative values of I1 and I2. We can say, for instance, that if V1 is less than V2, because this is a monotonically increasing curve, I2 should be bigger than I1. So if, say, V1 is less than V2, we have I1 should be less than I2. If V1 were equal to V2, so if they were at the same voltage, we would get the same current. I1 is equal to I2. And if V1 is greater than V2, then I1 is greater than I2. So we know something about the relative values of I1 and I2 based on the relative voltages across Q1 and Q2. So the transistor with the higher voltage across it will have the larger collector current. Okay, so that's one kind of thing we can say, would be the impact of having a finite early voltage. Another thing we can say, which is maybe slightly closer in spirit to our statement that I1 was equal to I2, we could say something like I1 is approximately I2 regardless of VB. So we turn that straight equal sign into a wiggly equal sign. And we say something like they're approximately equal to each other. And that's true. This is true. But we can actually do something that's maybe slightly better. So because this is pretty much a straight line, and we have defined the slope, we can say something like that the absolute value of the difference between the two currents is equal to the absolute value of the difference in the collector voltages divided by the slope of that, actually divided by RO, so multiplied by the slope of that line. Okay, you would do this by saying I1 is equal to IC0 times 1 plus V1 over VA. And we could say I2 is equal to IC0 plus, actually it would be I1 equals ICO plus V1 times RO, or rather over RO, because the slope is 1 over RO. And I2 is equal to ICO plus V2 over RO. And then we would take the difference of those two things and then put absolute value signs around it. And that's how we would get this. And if you recall, RO is equal to basically the run over the rise here, right? Because it's 1 over the slope. So the run here, if we go back to the x-axis intercept, is VA, and the rise is ICO. So that's equal to absolute value of V1 minus V2 over VA times ICO. And that's just basically rewriting RO as VA over ICO. Right, so RO, if you recall from our discussion of the early effect, was VA over ICO. It's just substituting that in if you like. That's fine. Now, ICO is going to be less than I1 and I2, just by virtue of the fact that we're out here and this is extrapolated back and it's actually less than all of the currents on this forward active part of the curve. And so in particular, the value that I see, or that I has halfway in between I1 and I2 is also greater than ICO. So we have here that this is less than, and I'm running out of room here, that this is less than or equal to the absolute value of V1 minus V2 over VA times half of I1 plus I2. Right, that just follows from the fact that ICO is less than this particular value, the average value between I1 and I2. And so we can divide both sides of this equation, or this inequality, by half of I1 plus I2, and that tells us, I'll just get myself a little more room up here. That tells us that I1 minus I2, absolute value divided by half of I1 plus I2, is less than or equal to the difference V1 minus V2 over the early voltage. Okay? So this is, on the left-hand side of this inequality, we have basically a percentage difference between the two currents. Okay, the absolute value of their difference divided by the average value. And that's bounded by the absolute value of the difference between V1 and V2 divided by the early voltage. And we can take this one step further and observe that the maximum difference that V1 and V2 can have is going to be bounded typically by the power supply voltage, right? So if my voltages in my system are strictly between the power supply rails, as they often are, then the maximum difference in the voltage I can have on the collectors of these two transistors would be bounded by VCC. So if V1 and V2 can be between 0 and VCC, then the maximum difference they could be is VCC. And so this is less than or equal to VCC over VA. So, and it's actually, there's some slop in here. I mean, this is actually strictly less than, probably, because we had this additional constraint that the two voltages had to exceed VCE sat. And so this would be less than or equal to, let's say, VCC minus VCE sat over VA. And since VCE sat is positive, we can make this strictly less than instead of less than or equal to. And this is kind of nice because it tells us that we know that the percentage difference between I1 and I2 is bounded by VCC. That's something we know about our system. VCC might be 5 volts divided by VA, which is an early voltage, which, you know, we've quoted typical values. Of maybe 25 volts. And so for a VCC value of, let's say 5 volts and VA of 25 volts, then these currents would not exceed 20% difference from each other. And that's kind of a nice thing to keep in mind. Because you may have some knowledge of the typical early voltage and your power supply, and you can say something like, well, even if there is a finite early effect, I know that if I have the same base emitter voltage on these two transistors, their collector currents are going to be, let's say, within 10% of each other, or within 15% of each other, or something like that. If you can constrain or bound the difference between the collector voltages to a tighter range, then you know something even better about the percentage difference between the two. But this would be a very conservative bound in the face of a finite early voltage and the difference between these two things. So we can basically say two different kinds of things when we have these kinds of matched transistors, but they have a finite early effect. One is that if the two voltages across the transistors are systematically different, there'll be a systematic difference in the same direction in the currents, and that can often allow us to predict something like systematic gain errors in our circuits and what effects those might have. And then there's also this idea that they're approximately equal to each other, and we can bound the difference with some additional knowledge about the likely amount by which the two voltages are different. But I find that this is a very handy kind of relationship to keep in mind. Okay, so that's going to be it for this segment. That we'll now take this pair of transistors that we've thought about and do some additional things with it to make it into an actual current mirror. We'll do that next time. See you next time.